What is going on, boys? Welcome to another episode of TrainMJ University Beta. Today, we're going to cover, we know muscles grow from anabolic steroid use, but how do they grow in the first place? Before we add in any chemistry, you got to understand the physiological natural process, because essentially what these anabolic steroids do is they enhance most, if not all, of the already pre-existing pathways of muscle growth. Okay? So there's three vectors, three pathways, if you will, to building skeletal muscle tissue. The muscle tissue I'm talking about is really made up of sarcomeres, which are the smallest unit of contractile fibers, including the tropomyosin and troponin, the myosin and the actin, and then of course the stroking of the oars motion to cause a muscle contraction. So how do we build muscle? And by build muscle as an adult, there's this concept of hypertrophy versus hyperplasia. Hypertrophy is the thickening of existing muscle fibers by adding in new contractile components within them. Hyperplasia is the addition of new muscle fibers. In adults, it is extremely unlikely, at least with current science and current understanding, to achieve hyperplasia. Very unlikely. There is a little bit of anecdotal belief, very, very scarce level of how strong this is actually true from a clinical standpoint, but there's a belief that certain protocols of drugs, which usually contain IGF-1 at extremely high doses, growth hormone and insulin at extremely high doses, and androgen at extremely high doses, if you ran that long enough and you somehow lived to tell the tale, perhaps you would garner some hyperplasia. But natural or not, the vast majority of any sort of muscle growth from bodybuilding in and of itself as an adult is going to come primarily from hypertrophy, the thickening of existing muscle fibers. The reason why people are so obsessed with hyperplasia is because they think it's some like permanent muscle growth, because once you have new muscle fibers, they're never going to go away. Perhaps this is true and maybe related to the muscle memory concept, which as you train, you not only gain muscle like thickness by adding in new contractile fibers, but you also gain or recruit myonuclei, nuclei, which are in all nucleated cells, including muscle fibers. Muscle fibers are actually unique in the sense that they have multiple nuclei, and that is reflected in muscle growth, which garners or actually constitutes not just the addition of contractile fibers to the existing muscles to make them thicker, bigger, stronger, but also the addition of new myonuclei. And they want to conserve, your body wants to conserve the myonuclear domain. The myonuclear domain being the ratio of myonuclei to muscle fibers. So hence in this aspect, someone that has trained and grown muscle, they might stop training for 10 years, but the idea is you still retain the myonuclei. And because of that, when you go back to training after 10 years of a hiatus, you'll likely be able to grow that muscle that you lost a lot faster. I'm not talking just like 50% faster, like it could literally be 2, 3, 4 times faster than ever before, okay, because of the myonuclear domain. But in terms of hyperplasia, like I said, super, super unlikely that you guys are going to actually achieve that, at least with modern day science. But it doesn't really matter because for bodybuilding purposes, who cares? You know, if you gain 10 pounds of muscle, who cares if it's from new muscle fibers or thicker muscle fibers? The fact is you have 10 more pounds of contractile muscle. Okay, that's all that matters. Now, there's three vectors, like I mentioned, to muscle growth. Those three vectors are mechanical tension, metabolic stress, and progressive overload. Mechanical tension is really how much tension and how much time under that tension are your muscles and tendons experiencing when you are training. And this is why we want to slow down or at least control the eccentric component of the lift, because that is where the most amount of muscle damage occurs. And therefore, by extension, the greatest amount of anabolic stimulus occurs from the mechanical tension. The second one is metabolic stress, aka the pump. So you go in the gym, you start training biceps, your biceps start to swell up with blood. Blood flow and metabolic rate meaning all of the anabolic and catabolic reactions at the biochemical level that are happening, that is your metabolism. And the rate at which those reactions are happening increases temporarily when you are training. As a result, you get more blood flow, more metabolism, more blood flow. What's in that blood flow though? Nutrients and signaling molecules, which are going to help build that muscle. What you're also doing with metabolic stress is you're swelling up the muscle tissue, specifically the muscle cells, the fascia, everything in there is swelling up. And there's this theory by a great scientist that is still active today. His name is Brad Schoenfeld. He's a professor at like Lehman College or something for like exercise science. And he outlines this concept of spatial priming. So think about it like this. If you're trying to fit as much muscle contractile fibers in a small amount of fascia, well, it's kind of hard to do that if it's only this big, right? But if you go in the gym, you get an insane pump that lasts for like hours after you train, and this is perhaps why you'd want to take like L-citrulline or L-arginine or even Viagra or Cialis, well, it's going to stay swelled up. And what that does is it causes additional space in the muscle for your body to actually be able to put in the new contractile fibers. That is spatial priming. And this is why metabolic stress is one of the three main vectors to achieving long-term muscle growth. Finally is the very well-known one, progressive overload. Going harder than last time, training longer than last time, shorter rest times between sets, right? It doesn't have to be more weight. It doesn't have to be more reps. It could simply be less rest time between sets. That in and of itself is a greater stimulus. You're progressing in some aspect. So those are the three pathways to muscle growth: mechanical tension, metabolic stress, and progressive overload. So going back to that metabolic stress and the spatial priming, we have two types of muscle hypertrophy. Hypertrophy meaning the thickening of existing muscle fibers, not the addition of new ones, but the thickening of already existing muscle fibers. And that hypertrophy can be further classified into two subclasses called myofibrillar hypertrophy and sarcoplasmic hypertrophy. The main difference between myofibrillar and sarcoplasmic hypertrophy is myofibrillar hypertrophy involves the thickening of contractile myofibrils. It's in the name. Again, the sarcoplasmic hypertrophy, sarcoplasm means the like the muscle cells like membrane is called the sarcoplasm, right? Kind of like the cytoplasm, like what's in it is the sarcoplasm. So it's basically all of the non-contractile units are growing. The cytoplasm, not the membrane, my bad. The membrane is called the sarcolemma, but the actual cytoplasm, the sarcoplasm of the muscle is growing. And a muscle cell is more than just the contractile sarcomeres. Like obviously that's a big part of it, but it still has nuclei, still has ribosomes, still has endoplasmic reticulum and a Golgi body, like things that you've learned from biology class. It still has those. And kind of like your heart having to adapt if you grow, right? These non-contractile components are still essential components of the muscle to maintain its life, for its survival, right? So you can't have myofibrillar hypertrophy without at least some sarcoplasmic hypertrophy. And what does sarcoplasmic hypertrophy do? Well, when you swell up that muscle with the metabolic stress and get a crazy pump, it again contributes to the spatial priming, therefore allowing or facilitating further myofibrillar hypertrophy. These two go hand in hand. Now, the type of training that you may be doing might err on the side of one or the other a little bit more. So, for example, if you're a power lifter with a weight cap, you wouldn't want big, swelly muscles that don't produce a lot of force. So you probably train at a really, really high intensity and low amount of reps to garner more myofibrillar hypertrophy, at least in theory. Now, if you're a bodybuilder, you want to maximize both because who the fuck cares how much you can lift? It only matters how much you look like you can lift, right? So both myofibrillar and sarcoplasmic hypertrophy are important, but it doesn't really matter because if you do a good training program, a good diet, good supplement, and drug stack, you're going to achieve both anyways. But this is just kind of outlining what's really happening at the cellular level. So when you go and train in the gym, and I'll try to make this brief because a couple of years ago, I did like 2-year long research study on like outlining every single pathway to muscle growth. So this is like the synopsis of it, okay? What is exercise? Well, exercise is a stress, and it's a stress because there is body tissue damage that is occurring. And this is good. Like usually you wouldn't want body damage. You don't want chronic inflammation. You don't want systemic inflammation. But local inflammation, inflammation being the primary stimulus to any sort of body damage, including resistance training, is important because that is what's going to kickstart the adaptation, the healing process. No inflammation, no gains. Inflammation is the signal for your body to produce more gains if you have the resources, nutrient-wise, and the recovery and the hormones, okay? And this is actually proven in the science. If you were to take a non-steroidal anti-inflammatory drug, such as ibuprofen, such as aspirin, at a high dose, right before or right after your training, right around the workout, you're going to significantly diminish the gains you get from that workout. You might not get so sore from the workout, but you would drastically reduce the inflammation, even if you trained hard, because you're taking an anti-inflammatory drug. And because of that, there's a very statistically significant difference between the muscle growth that you gain when you're on the non-steroidal anti-inflammatory drugs versus when you're not taking those things. So if you can help it, stay away from those drugs as much as possible, especially right before, right after training. Once inflammation happens, well, every single tissue in your body adapts to stress. But depending on the tissue, it's going to adapt to that stress, that specific stress, differently. And it will do so, it will choose the adaptation that makes the most sense for survival. For example, your bones. Well, as an adult, your bones are going to get bigger from mechanical stresses, but they absolutely can get denser. That is the bone's way of adapting to mechanical stress. Now, on the other hand, with muscles, the primary job of a muscle is to move loads, contract, move, right? Well, in that case, the most evolutionary sound adaptation to muscle damage that was caused by load is to create an adaptation that helps it prepare for future additional loads, aka in muscles, that is the muscle hypertrophy. Because now the muscle is bigger, and therefore, because of the higher cross-sectional area of the muscle, it can by definition generate a higher peak force, a higher contractile force, and overcome whatever the thing you were trying to move in the first place. And this is why when you start lifting, 225 might be super hard in the beginning, but then after some time, your muscles grow from myofibrillar and sarcoplasmic hypertrophy. And now the 225 is a lot easier to move because you're working with a bigger, stronger muscle. Once inflammation happens in the muscle, to kickstart this process of muscle rehab first, get back to baseline, and then some, the and then some is the muscle growth, what happens is many things. And these all happen at the same time. I'm going to go over the main things that happen. In your body, especially when you're young, but also when you're older, you have things called stem cells. And there's a ton of research on regenerative medicine, on stem cells. But even without the regenerative medicine or some like random procedure that costs $50,000, like that's actually how much it costs, you still have stem cells in your body. And stem cells are multipotent or pluripotent, meaning if you break down that word, they have a potential to turn into any different cell that your body needs. Turn into meaning differentiate. So for example, a stem cell, if given stimulus A, it might differentiate into a bone cell, an osteocyte. A stem cell given a different stimulus, stimulus B, might be differentiating into a hepatocyte, a liver cell. And then of course, in the muscles, we have something called satellite cells. Satellite cells are basically one step after stem cells, and they are unipotent. Unipotent meaning they have the potential to turn into only one thing. Uni is one, right? And that one thing is adding to the muscles themselves, right? So what happens is when you break down the muscle and there's inflammation happening very shortly after, perhaps even during the process of inflammation, the satellite cells, and they're called satellites because like planets that have satellites, they're right around the muscles. They're right around the muscles that you just trained. All your muscles have them, right? They get activated because without muscle training, without resistance training, they're going to be in a dormant state. Like, why would your body build muscle unless it has a stimulus to do so? Well, now you go ahead and train the gym. You have given that body the reason to activate those stem cells, to use those resources, to activate and recruit and differentiate those satellite cells. Now, before the satellite cells like turn into myofibrils to be added on to the existing muscle cell to heal it, it's going to go through multiple processes. It needs to first commit to the myogenic lineage, and then it needs to kind of express a bunch of these myogenic regulatory factors. This is kind of how your body knows what to do with what, right? You have so many different things your body could do to adapt. The question is, what's going to make the most sense for me right now? So given you've trained properly, you're eating properly, your hormones are in check, and you just completed a workout, well, now you've activated those satellite cells, and they're committed to the myogenic lineage, committed to turning into muscles. Once they have committed, assuming you have the proper nutrients and the resources and the growth factors involved, they proliferate. They proliferate meaning they divide and replicate. And then they kind of fuse with each other to create this contractile component. And then that contractile component binds to or fuses into the existing damaged muscle. And if you do that enough, you're not only getting your muscle that you just damaged back to baseline, but assuming you have the proper nutrients and hormones in place, it will actually overcompensate for that damage. And that difference, like I said before, is the tangible muscle growth that you're looking at. Satellite cells. Other biochemical pathways exist as well, besides just the satellite cells, but they're also involved in the satellite cell process, right? So, for example, if you're going to proliferate a cell, well, what are cells primarily made out of? Proteins, right? Proteins. Meaning, if you're going to do this thing called satellite cell proliferation, you have to increase your rate of protein synthesis, at least temporarily, to the extent enough where you're going to get enough satellite cell proliferation to cause that differentiation and fusion into the damaged muscle cell. Well, that protein synthesis complex is so important for muscle growth. Okay? And the primary biochemical pathway that all of these different ones ultimately kind of conjoin into to cause that increase in protein synthesis, that junction is called mTOR, the mammalian target of rapamycin. If you activate mTOR, mTOR activates an effector called S6K, and that is protein synthesis. Now, by activating mTOR, you're only turning on protein synthesis. You're only telling the construction workers to go ahead and build. But unless you have the building blocks, like the cement, like the wood, like the nails, right? All the different resources that you need, it's not going to actually build muscle with just the stimulus. You need the stimulus plus the building blocks, aka the nutrients. And that's where whole foods on a regular basis comes into play. Besides mTOR, kind of upstream, downstream, crosstalk with each other, right? All of these things are happening at the same time. It's a very big orchestration process. There's other biochemical pathways that are involved and actually important. So for example, one of them is the WNT, the wingless integrated something, frizzled receptor. FCD is this canonical receptor. Canonical meaning like it's the main one. Okay. Now there's a WNT FCD pathway that's the canonical arm and then the non-canonical arm. Both of them are still important. But in essence, the main takeaway here is the canonical WNT FCD pathway involves the beta-catenin protein or the molecule, beta-catenin molecule. The non-canonical one does not, at least not directly. But the purpose of WNT FCD is for structure manipulation of the satellite cell. So like I said, when you cause inflammation and damage in the muscle, what you're doing is you are now activating the satellite cells. They're no longer in that quiescent dormant state. They've woken up and they're like, okay, let's do this. Let's build some muscle, right? Let's go help this guy out, the guy being the muscle that you just damaged, right? Well, to do that, you need protein synthesis because you're building new cells. Cells are made out of protein. But you also need to essentially facilitate the process of the cell growing and the cell dividing and then having those divided parts moving towards and binding to and fusing to the damaged muscle cell, right? What covers that? That is the WNT FCD pathways, both the canonical and non-canonical. They affect the cytoskeletal organization of the cell. In extension, affecting the cell's polarity. Polarity meaning, for example, like if you have a magnet, you have a north side and then you have a south side, right? They don't repel each other. They would bind to each other, and then if you have north side and north side together, like the same one, they would repel each other, right? So it affects the polarity of the cell, of the satellite cell, so that it basically optimizes the satellite cells that are going to divide and differentiate the muscle fibers, while also governing the satellite cells that'll just stay as satellite cells so that you don't lose all of your satellite cells because you have a pool. You have a limited amount of these satellite cells. You wouldn't want all of them to just turn into muscle cells. You want some of them to do that, but you want enough left so that you can do more muscle growth later, right? So this is where WNT-FCD happens, right? It's the cytoskeletal organization and the cell's polarity, which ultimately help it divide and not deplete the satellite cell stem cell pool, but also causing enough of those satellite cells to proliferate, differentiate into muscle fibers and actually bind and fuse to help the muscles move because of their polarity, of their motility, the mobility of the cell, the ability of the cell to move from the satellite cell location to the actual damaged muscle fiber that you're trying to grow in the first place. Okay, so that's WNT-FCD beta-catenin for you. MAPK. MAPK is the other one that is very, very important to understand in terms of biochemical processes. MAPK is essentially the most important mechanotransducer junction. Mechanotransducer meaning mechanical stimulus, transducer. transmitting a biochemical signal to cause a certain effect, in this case, muscle growth. Now, there's various MAPK pathways. I mean, this is a huge family. But the three most important arms of that MAPK pathway are ERK, extracellular related kinase, kinase meaning like an enzyme affecting like ATP phosphorylation, P38, and JNK, C-joint N-terminal kinase or whatever. Okay, so these three, the ERK, the P38, and the JNK, are the three most important arms of the MAPK family when it comes to protein synthesis and muscle growth. So what MAPK is essentially doing via these three arms is it's sensing the mechanical stimulus of you lifting. Besides even the fact that the muscle is getting damaged, but simply the mechanical stimulus, this is where the mechanical tension comes in. Simply by sensing mechanical tension, it's going to activate MAPK. Okay? Now, there's a very important part about this. Okay? There's three arms of the MAPK. If you activate all three arms of MAPK, P38, ERK, and JNK, it will cause a lot of effects. The two main effects are fatty acid oxidation, so fat burning. Obviously, if you're training, you're burning some fat. And also, it will affect gene transcription. But this is only the case if you are activating all three arms of the MAPK. And the reason you want to affect gene transcription is because, well, when you affect gene transcription, you affect protein translation. And protein is what your muscles are primarily made out of, right? So this is another way that you're getting protein synthesis. Well, here's the catch. If you train really hard, like beyond a certain level of intensity, like basically at or near failure, you're pretty much going to guarantee you get both of those. You get both the fat burning and you get the gene transcription protein expression because the stress has reached a threshold of intensity where your body has determined, oh, this stress is big enough where I need to adapt. I need to change. I need to get bigger. I need to get stronger. I need to build more muscle. This is why intensity is key. If you don't train very hard, or if you're kind of just going through the motions, unfortunately, you only activate one out of those three vectors. I believe the one you activate is P38, but don't quote me on it. I'm pretty sure it's only one, and the one is P38. If you don't train hard, or if you never change your training program, you do the same thing again and again, your body doesn't have a reason to adapt. And the reason it doesn't have a reason to adapt is because when you only activate one arm of the MAPK pathways, you only get fatty acid oxidation. You just burn fat. So by definition, when you're going through the motions, you're really just going through the motions. You're not causing any muscle growth. This is why, on occasion, changing your gym, changing your training program, really going balls to the walls and maybe pulling back, this is favorable compared to doing the same old every single day. Because at some point, your body is going to be like, oh, you're not hitting this threshold of intensity anymore. I have no reason to tap into my gene transcription and affect my protein translation. I'm going to stay the same, okay? Now, going back to mTOR. When you activate mTOR, you're not only turning on protein synthesis, but you're turning off protein breakdown, catabolism. Now, things that activate mTOR are very broad. A lot of these pathways that we just discussed, from the WNT-FCD pathways to the beta-catenin to the MAPK-ERK pathways, and even the inflammation in itself, inflammation pathway really being affected to the NF-kappa B pathway. That's like the main inflammation pathway at the biochemical level. All of these pretty much ultimately increase protein synthesis by somehow, some way, cross-talking with the mTOR pathway. Okay? So beyond those, things like simply protein consumption, specifically amino acids such as arginine, such as leucine especially, they can directly activate mTOR. Another supplement that you might be familiar with, maybe you are, maybe you aren't, HMB. It's like beta-hydroxy beta-methylbutyrate or something. It's like a big muscle builder supplement on Amazon. Does it work? No, not really in terms of like actual muscle gains. But can it activate mTOR? Yes. Can BCAAs activate mTOR? Yes. But like I said, turning on mTOR in and of itself, not enough for muscle growth. You need the building blocks. You need not just the construction workers that are willing to work, but you need the construction tools and the equipment to actually make that happen. This is where a broad spectrum of amino acids, making sure that you're getting all of your essential amino acids is so important. Because if you don't have all your essential amino acids, you can turn on mTOR all you want, but it's not going to cause any muscle growth. The workers in your muscle cells are going to be like, yo, we are ready to work, let's do this. But there's no cement, there's no nails, there's no wood. Okay, so you need a full spectrum protein source. Growth factors in general will also activate mTOR. Things like IGF-1, things like MGF, things like VEGF, BDNF, NGF. There's like so many of them. Okay. But anyways, your main ones for mTOR, at least in terms of bodybuilding, are amino acids, which come from the proteins after you digest them and absorb them. It also comes from IGF-1 and insulin. Insulin being a very potent stimulator of mTOR. Now, like I said, when you activate mTOR, you're turning on protein synthesis, or you're turning off protein breakdown. You're turning off the catabolism of proteins. Evolutionarily, this makes sense because if you're going to do something like growing muscles, it's usually in a fed state, right? So when you're eating food or right after you eat food, your body is in that digest and rest and absorb kind of state, right? Well, it doesn't make any sense for your body to catabolize anything like body fat or even muscle mass because you have a surplus of nutrients, at least transiently during that time right after you ate, postprandially, like right after you ate. So increasing mTOR stimulation will absolutely, given the right foods, given the right hormones, cause more muscle growth. But there's a problem with this if you do it too much, okay? So this is where something called the IGF-1 trade-off kind of comes in. And I'll probably talk about this more in later videos, but this video is getting already pretty long, so I'll try to keep it short. The IGF-1 trade-off is this. IGF-1 is known as one of the most important, probably not the most important, but it's one of the most important hormones for muscle growth. And part of the way that a lot of these anabolic steroids work is by increasing IGF-1 sensitivity as well as availability as well as literal production of the IGF-1 itself. Okay? Well, when you increase IGF-1 and thereby by extension increase mTOR activation, you're turning on protein synthesis, but you're turning off protein breakdown. So it's great for muscle growth, but you're missing out on protein breakdown. Now, why do I say missing out on, as if it's a bad thing? Well, if it's chronic and all the time you're turning on mTOR, I mean, a great example of that would be cancer, but another great example would be if you're eating around the clock, like a bodybuilder, as you should, all the time, high protein meals, high carb meals, right? You're turning on mTOR, turning on mTOR, turning on mTOR. You're never really turning off mTOR. It means that you're really never really turning off protein catabolism. You're never breaking down protein. Now, you might think as a bodybuilder, this is like the best thing ever. Like, why would I ever want to break down proteins? My muscles are protein. I want more protein synthesis. I don't want any protein catabolism. But here's the catch, right? Here's the catch about IGF-1 trade-off. When you chronically stimulate mTOR, you're missing out on a very, very essential process called autophagy. Autophagy is a naturally occurring cellular process where your body basically goes through and gets rid of, or at least recycles, damaged cellular components and proteins and organelles. Organelles being the things that cells are made out of, like the Golgi body and the ribosomes and whatever. Right? These cells, they don't last forever, right? There's like a statement, all your cells in the body replenish themselves every 7 years or something like that. Who knows whether that's true or not? But the point is, there's always a constant turnover rate, right? The old cells are replaced by new, healthier cells because old cells are, I mean, they're dysfunctional, right? They've accumulated a lot of damage to the proteins, and therefore they might be dysfunctional. If that's too much, you're causing an increase of risk of cancer. But when it comes to autophagy, you need some autophagy, right? You need some autophagy because without autophagy, your longevity goes down. Your longevity goes down. Because what autophagy does is it gets rid of all the bullshit in your body that you're accumulating simply by existing, simply by metabolizing food, by metabolizing air, like cellular respiration. You're causing oxidative stress, and because of that, you're causing cellular damage over time. This is aging. This is aging. Autophagy reverses that, at least to some extent. So here's the trade-off, the IGF-1 trade-off that we're talking about. If you redline IGF-1, you're erring on the side of performance, but you're gonna miss out on longevity because you're never really getting enough autophagy. So technically, the best way that we know so far naturally to extend your life would be to pretty much minimize mTOR stimulation, would be to pretty much be fasting all the time, eat minimal calories, barely eat any protein, or just enough to like replenish what you need. But besides that, fasting is probably the best known way naturally to increase your lifespan, right? So that's the trade-off here. It's, do you want to be huge, right, for like a little bit, or do you want to live a really, really long time and probably be super healthy for most of it, but you'll never be jacked? So that's kind of the balance here, right? You don't have to choose one or the other, but understand that it's a spectrum. And this is why, if you look at bodybuilding, you have men's physique, the smallest ones, right? I mean, I'm sure there's smaller ones than that, but let's be real, like it's not, no one cares about the ones that are smaller, okay, like no offense, but you got men's physique, you got classic physique, which is kind of in the middle, and then you got open bodybuilding, right? So like 260, 270, 280 shredded on stage, absolute monsters, like mass monsters, right? Well, the more body weight that you have, whether it's muscle or not, the side effects from the drugs aside, simply the amount of food that you have to eat to get to that mass monster level is going to be detrimental to your longevity and health, because to do that, you would literally have to eat around the clock, every single 2 to 3 hours, 3 hours at the very most, high protein meals. Guys, it's not uncommon for pro bodybuilders at the open level, especially on the Olympia stage, to be routinely killing 500 to 600 grams of protein a day. Not vegan protein, real protein, okay? Is that great for muscle growth? Yes, assuming you don't die from like GI issues. But is that good for longevity? No, because you're constantly redlining mTOR, and because of that, you're constantly not doing any autophagy, and you're going to suffer long-term longevity issues as a result because you're redlining IGF-1, okay? So yeah, this is a pretty long video. Hopefully this was helpful, and I'll see you guys on the next one. But main takeaway from this video, aside from everything I just said, is all of this stuff that I just mentioned, from the metabolic stress to the progressive overload to the myofibrillary sarcoplasmic hypertrophy, satellite cell activation, WNTFCD, beta-catenin, mTOR, MAPK, all this stuff, it happens naturally. Naturally, okay, it's going to happen naturally, men and women. But when you take anabolics, it just enhances everything. So you get more satellite cell activation, you get more inflammation for the beneficial process of muscle growth, you get more mTOR stimulation, especially from the same amount of protein that you eat. Okay, so this is basically how muscles are grown. And it doesn't matter whether you're natural or not. This is still the same pathways. It's just when you're enhanced, it's accelerating all these processes more. Hopefully that makes sense, guys. I'll see you.